Hi class, in this lecture here we want to now talk about an application of differentiation called a summary of curve sketching. And what this basically does is this section is going to take all the topics we've learned about so far and put it together to analyze a function and then use that information to sketch the graph of the function. Okay, so here's what we're going to do in this section, just one thing. Okay, we're going to discuss how you analyze and sketch the graph of a function. And you're going to notice that these examples are going to be rather lengthy, okay? So here's what we've discussed so far, okay? A lot's been going on. We've discussed continuity, vertical and horizontal asymptotes, differentiability, relative extrema, or relative extreme values, increasing and decreasing functions, concavity, and infinite limits at infinity. Okay, so now what we're going to do is we're going to be given a function, and we're going to find all the above information from it, and then we're going to sketch the curve. All right, so these examples are going to take a while to do, so here's what I'm going to do. I'm going to work through 4 examples in this lecture, in this section, okay? I'm going to do one example of a polynomial function, a rational function, a trig function, and then some transcendental function. And what I'm going to do is I'm going to break up the lecture videos for each example. So this first lecture video here is just going to be a very, very simple polynomial function. All right. So what we're going to do are the guidelines we're going to work through for this. Okay, we're going to follow these steps here. First thing we're going to do is we're going to determine the range and domain of the function. Then we're going to determine the intercepts and the asymptotes. And then we're going to use the first derivative to determine the intervals the function is increasing and decreasing. And then you'll notice I'll use the first derivative test to find and identify relative extrema. Then we're going to use the second derivative test to determine intervals the function is concave upward, concave downward, and points of inflection. And then what we're going to do is we're going to use all this above information to sketch the graph of the function. And then what I'll do after I sketch it by hand, you're going to notice then what I'm going to do is I'm going to use a graphing utility to verify my results. So I'll check my graphing calculator and we'll see how I did. All right, so let's jump into this one, okay? So this lecture video here is just going to be a very, very simple polynomial function. So here's the function we're going to be given. Okay, so our first example. Sketch the graph of f of x is equal to x cubed minus x, okay? Using the guidelines in this section. Okay, so the first thing, just going back, determine range and domain. Well, this is a polynomial function, so the domain is negative infinity to infinity. And then the range as well, okay, is a polynomial function here, so this is negative infinity to infinity. Okay, so that's pretty easy. Are there any asymptotes for this type of polynomial function? No, there is no asymptotes, right? We know that about a polynomial function. Okay, we'll do an example later on where there will be asymptotes. All right, so let's find the intercepts, okay? So the y-intercept, okay, that occurs at 0, f of 0. Right, you know, the y-intercept occurs where x is equal to 0. Well, if you plug 0 into this function, you get 0. So the y-intercept is the origin. That's great. Now the x-intercepts. Okay. This occurs where f of x, which is this, is equal to 0. All right, so what we're going to do is we're going to have to solve this. So I'm going to factor out an x. Well, x squared minus 1 is the difference of 2 squares. So that factors as x plus 1 times x minus 1. And look, you can see here, right, the values that will make this equal to 0 are either 0, -1, or 1. Okay? So here, a bit of a typo there. So here I have 3 three x-intercepts, okay? So if it helps to see it, the points of the x-intercepts are -1, 0, 0, 0, which is also the y-intercept, and 1, 0. All right, those are going to be really important to help me sketch the graph of this function. Okay, we're getting there. We're getting there. So the next thing we're going to do is we're going to do all the first derivative stuff. Okay, so that's going to be increasing, decreasing, and that's going to help us find relative extrema. All right, so now we're going to look at the first derivative. Okay, and this is for increasing and decreasing. And then relative extrema. All right, so this was our function, f of x, which was x cubed minus x. So f prime of x here, it ends up just being 3x squared minus 1. So you're going to look for critical numbers. So those occur where the first derivative is equal to 0. So I'd add the 1 over, divide by 3, and then take the square root to solve. So you get x, you have two critical numbers. X is equal to plus or minus the square root of 3. So here, right, this is square root of 1 over the square root of 3, and I'll rationalize the denominator here. All right, so just to help here, this is approximately, because I'm going to use this to approximate here, 0.577 roughly. Okay, I'll use that to help me approximate this when I go to sketch the graph by hand. All right, so then I've got the critical number. So then what I'm going to do now is I'm going to set up my intervals, okay? So I'm going to go from negative infinity to this first one here, negative the square root of 3 over 3. Then I'm going to go from negative the square root of 3 over 3 to positive the square root of 3 over 3. And then I'm going to go from the square root of 3 over 3 to infinity. Then I'm going to pick test values in the interval. So, here I'll pick -1, 0, and I'll pick 1. And then you're just going to look at the sign of f prime of x at the test value. Well, if you plug -1 into the first derivative, right, -1 squared is 1 times 3 minus 1, that's positive. If you plug in 0, you just get -1. And then if you plug in 1, you get a positive again. So look, you can see it's increasing on this interval and this interval. So increasing on negative infinity to the negative square root of 3 over 3, and on square root of 3 over 3 to infinity. And then it's decreasing on this middle interval, negative the square root of 3 over 3 to the square root of 3 over 3. Now what's also great is you can use the first derivative test to find relative extrema. So increasing to decreasing, we have a relative max at this point, at negative the square root of 3 over 3 comma f of negative the square root of 3 over 3, which, just to help me plot it, is roughly the point -0.577 comma to roughly 0.385. I'll let you verify that yourself in a calculator. Okay. Then we have a relative min because it's going for increasing. At this square root of 3 over 3, comma, f of square root of 3 over 3. Which is going to be roughly the point 0.577, comma, negative 0.385. All right, we're getting there. We're getting there. So this is really important here. We know where it's increasing, decreasing. These relative extrema tell us the turning points of the graph. So then what we're just going to do next is we're just going to do the second derivative stuff just to have it. But you'll notice when I go to curve sketch, it's really hard by hand to sketch concavity. And it takes a lot of practice. So I'm going to focus mostly when I sketch is like on the intercepts, the extrema, increasing and decreasing. But I'm still going to find the second derivative analysis just to have it. All right, so here's the first derivative right here. So now on the next one, now let's look at f double prime of x for concavity and points of inflection. All right, so f of x was x cubed minus x. We saw f prime of x then was 3x squared minus 1. That means f double prime of x is just 6x. So we're going to look, where does f double prime of x equals 0? This occurs at when x is equal to 0, right? The only way you can have 6x equals 0 is when x is equal to 0. So then again, you're just going to use this to set up your interval, right? You only have one here, one value. So your interval is going to go from negative infinity to 0, and then from 0 to infinity. So you're going to pick up a test value now, which will be negative 1 and 1. No, just the easiest numbers. Then you're going to look at sine of f double prime of x at the test value. Well, this is really easy, right? If you plug a negative in here, negative 1 in here, you get a negative. If you plug a positive in here, you get a positive. So what we see here, okay, because sine of second derivative is negative in this interval, we're concave downward on this interval, negative infinity to 0. And we're concave upward on this interval, 0 to infinity. So when we change concavity from concave downward to concave upward here, that means we have a point of inflection. And it occurs when x is equal to 0. Which is just both an x and y intercept here at the origin. And that's okay. All right, so now the fun begins. Okay, we want to take all this information, and I want to sketch the curve. And I'm going to do this by hand. I'm going to show you how to do this. All right. So it's the sketch of f of x is equal to x cubed minus x. One, two, three. 1, 2, 3. I'm picking this scale here because a lot is happening at really small x values here. So I don't want to know too much or go out too far. All right, so I'm going to plot the intercepts, right? So here's an intercept, here's an intercept, here's an intercept, right? At negative 1, 0, and 1, okay? Next, I'm going to eyeball the extrema, okay? So I have a relative max at negative 0.577, comma, 0.385. All right. So that's over here, and I don't know, roughly here. I'm just super eyeballing it. All right, so I know that that's going to be a max. And then here I have a min at 0.577, negative 0.385. So I don't know, it's roughly here. So that means that's a min, okay? Well, look, it's increasing from negative infinity to this point, the max, and then it's decreasing. I got to go through the intercepts till here, and then it's increasing here, and then it's just a polynomial we know goes like that. All right, let's check our graphing utility here and see if my graphing utility produces this same graph. So let's look at x cubed minus x, right? Yeah, and look, and I'll even zoom in a little. Yeah, you can see this is exactly what I have here. Well, not exactly. I mean, you know, a lot of this is eyeballed, but yeah, I've got it great here. So you can see here what we're going to be doing is we're using all this information to help us sketch this graph. And then at the end, what you should do is, you know, then check your graphing utility, see if you did it right. And if you didn't, you know, go back and see where you might have made a mistake. All right, so I'm going to continue this lecture with more and more examples just so you can have a good understanding of this process. And, you know, the first and second derivative stuff is a great review for this.